Good morning, good afternoon, and good night, SAFIR community. So I'm very honoured to be presenting at today's webinar, SAFIR Day. And what I wanted to talk about today were copebacks when considering steel hollows. And what I'd like to do to start with is just give you a rundown of what the presentation will cover. And I think it's important that we start with what is a copeback. So I'll start with a couple of slides just on the background of copebacks. And then I'd like to dive into a real project where we did 3D thermal modeling using SAFIR to look at emitting copebacks entirely from a project. And then off the back of that work we did on a project, I'd then like to go into a bit of research we've done using 2D thermal modeling with SAFIR in a parametric study. And then talk about some of the insights and next steps off the back of that as well. So, what is a copeback? So a lot of SAFIR users we know very well a steel bay, and we might well have columns, primary beams, and secondary beams. And it might be possible to emit the protection to those secondary beams when looking at tensile membrane action. So we might well have a situation where we have emitted the protection to those secondaries. But what we have to be mindful of is those unprotected secondaries, if not protected, will transmit quite a lot of heat into those localized areas. So currently, best practice would ask us to add what is known as a copeback. This is an extension of the PFP material onto the secondary element. What I'm showing you now at the bottom of this image here, this is a typical copeback detail, and this comes from the document FABIC Technical Note 13. So this is primarily for hydrocarbon fire scenarios. But effectively, what it recommends you do is you extend the protection back onto the secondary element, in this case, 450 millimeters. A key aspect of this is you're actually applying the thickness of the primary steel, not the thickness required for the secondary, back onto the secondary. And just to have a look at a bit of the history of where this guidance came from, back in 1996, there was a joint industry project, and the SCI did some thermal modeling of copebacks for the hydrocarbon or petrochemical industries. So if anybody's interested, RT 543. And it was a document designed for determination of copeback thicknesses. But one of the findings of that research was that at 450 millimeters, there wasn't much additional heating into the primary element. So deemed that a copeback of 450 would be safe. Later, that was then adopted in FABIC Technical Note 13, again recommending 450 millimeter copebacks. And then later, for cellulosic fire scenarios, UL released a best practice guide recommending 450 for cellulosic fires, deemed that because the fire scenario from the standard hydrocarbon curve to the cellulosic is less severe in terms of heating, that the 450 would also be applicable. The ASFP, based out in the UK, decided also to use a similar copeback distance of 500 millimeters. But you can see that there's everybody's been adopting a very similar copeback length in the industry. But a lot of these documents do mention that you can determine a different length of copeback and potentially emit them completely. So this now moves on to sort of our project that we did some 3D thermal modeling to try look at actually emitting copebacks. So this is the project BB7 we're appointed on. This is a large project in Leeds in the UK. It's got a number of buildings. We've got commercial buildings, offices, residential, car parks, so buildings of that nature, but all steel composite construction. Now, one of the buildings, the car park, which you can see highlighted here, needed R60 or 60-minute fire duration. But around the perimeter columns, there were fitting crash barriers. These crash barriers are not necessarily structural. If you took them out, the structure would remain standing. But as per the best practice recommendations, a copeback of 500 millimeters would be required to limit the heat transfer into those primary columns. So the question that we were asked is, can we look to actually emit those? Just to give you a better understanding of how it actually looked, if we look at it from a 3D perspective, we have an I-section column, so there were varying sizes across the project. And then you had the handrail and the crash barrier. which would be, in this case, unprotected. And these barriers and crash handrails, they actually frame into a protected plate that frames across the two fletched toes. So that plate itself will be protected, but the handrail and the fixing for the crash barrier would not. Now, you might ask, 500 millimeters doesn't sound like a very large amount of cost when we look at it from a perspective of application, but because this is a crash barrier, there's likely going to be a lot of damage to these areas. And as it's on the perimeter, it's quite hard to get up to those levels to apply any fire protection material to those systems. So there was definitely an appetite to try and knit the coat back entirely, just so that through the lifespan of the building, constant repairs wouldn't be needed every time a car bumped into one of the crash barriers. So this is sort of the 3D model we were looking at, and maybe this will be a little bit more clear of what we did. We took a line of symmetry through the column, and in the model we put a control column. So this column on the left was just a fully protected column with nothing else framing into it, no extra heating. The column on the right is the one that has the protection, the toe plates, as well as the unprotected hollows. Now, we encountered an issue at this stage. If we look at the technical documentation of SAFIR, we know that we need to account for the cavity within the hollows. But at the moment, we only have the ability to model voids or these cavities in 2D. So we needed to come up with a way of dealing with this. And what we wound up doing was we actually did a 2D segment through. So you've got the hollow framing into the plate and the section. So we applied a void within the hollow and then the standard FISO boundary condition to the rest of the element. We then ran another model where we'd remove the void. What we did instead is we applied the ISO curve directly to the inside of the column to try emulate the extra heating we would have got from the void. We were expecting to actually lower the intensity of the fire until we got the same results. But as it happened, doing this, we only observed a 20-degree increase in the actual primary element. So we deemed that this was actually quite a conservative way of dealing with the fact we couldn't model a void in 3 dimensions, and decided to put the ISO curve directly as sort of a conservative estimate of what the void might do in terms of heating. So we carried out that study on a number of columns, and we created a parametric model so we could change the size of the columns, and we could also change the critical temperature of the primary hollow. Oh, sorry, the primary eye section, sorry. And what we found was that if we were to over-insulate the primary element, it actually counteracted the additional heating you would see from the secondary. So the graph you're seeing here, we have the control temperature, so that's the column with nothing in, and the test, which had the non-protected secondary attachments into it. And what we found that if you insulated the column to 450 degrees, the average temperature of the primary would reach 500 degrees. And so on. If you protected at 500, it would get to 540. And so based on the utilizations of the actual column profiles, we were able to offer a modified critical temperature where the effects of that additional heating were mitigated. So job done. We managed to, in some cases on that project, eliminate the coat backs by over-insulating the primary. But some we didn't, and as we were curious, as most of us are in this industry, we just wanted to check that the 500 millimeter coat back would work. And then I want to lead on to sort of research that we decided to carry out based on those results. So what we did was we wanted to get the void constraint back into the model, and we created a simple 2D model where effectively we had a control element, a test crash barrier, a test handrail. We had primary elements, which are just emulated as plates here, just a protected plate, and then the secondary hollows here. So you can see the crash barrier was slightly wider than the handrail. And in this instance, we actually implicitly modeled the intumescent coating around the profile of 500 millimeters. We then added the FISO curve to the outside and applied the void constraint. We also, because it was an eye section column and it was a hollow framing in, we also reduced the protection on the hollow, as intumescents typically for the same DFT do not behave as well for a hollow as they would for an I section. So basically the same DFT would not provide the same insulation for nearly all intumescents on the market. So we accounted for that in the model. So we ran a model at 60 minutes, which was a fire scenario we had on the project, but we also ran one at 120 minutes just for curiosity. And what we found for the R60 model is that the end plate, the primary element, achieved about 509, 501. So we weren't particularly concerned. The coat back seemed to be doing what we needed it to do. However, for the R120 profile, we were seeing temperatures as high as 626 degrees in the primary and 563 degrees in the handrail, which are way above what we'd have expected. And we would be concerned that there could have been premature failure in those profiles at R120. But yet we had applied the best practice guidance of 500 millimeters. So we wanted to understand this a bit better. What are we seeing here? We also wanted to understand why, for the same protection, are we seeing 526 for the crash barrier and 563, a significantly lower temperature, for handrail. And if you go back to the work that was done by the SCI, you will note that all the coat back distances are based on a secondary I section framing into a primary. There was never actually a study done on hollows framing in. So this void constraint might well not have been covered in the original research that was done. So we were interested again. We decided we'd run a few tests on just varying the width of the hollow, but leaving everything else as per the original SAFIR model. And we got some quite interesting results. We actually found that as the hollow width increased, the average heating within the primary began to escalate quite quickly. So we were seeing at a hollow of about 75 millimeter diameter, would have added, say, 120 degrees as an average. But at 400, you might have been getting 450 degrees added into that primary section. Quite an astounding amount of additional heating for a 500 millimeter coat back. We believe this is related to the view factor based on a 90-degree angle. So we're assuming that we're getting quite a similar trend that we would expect for a view factor, which is how the void constraint works. So we think we're seeing this phenomenon in the model. But I realize we've got a SAFIR community, so I'd be interested to hear if there'll be agreement with that sort of statement. But we wanted to understand this even further, and as with all things, we needed to go into a parametric model to get as many different orientations, steel sizes, and parameters modeled. So what we did is we looked at a few steel sizes, 6.3, 12.5, and 20 millimeters for both the primary and the secondary. We changed the height of the primary element, so effectively emulating centers of unprotected profiles at 250, 500, and 1,000 millimeters. We looked at varying coat back lengths, 500, 1,000, and 2,000. And we also changed the width of the hollow. And we also looked at temperatures of 500 and 600 degrees and for a variety of different fire durations, 60, 90, and 20. And this was only for cellulosic fires. We haven't looked at this for hydrocarbon just yet, but we thought this was a large enough sample size to sort of see what was going on and see if we could find any trends. To make it a little bit easier for ourselves, the 2D model we created actually had a control, so we could check that the performance coating was working on a unaffected profile, and then 9 others looking at different coat back lengths and different widths of hollows. So one model did 10 samples. So in the end, we wound up with 108 infiles and 972 samples to sort of investigate. Too much for a human to do quickly. So I'm very fortunate that my team was able to write some Python code to automate getting the material properties changed, creating the infiles, and also extracting the data from all of those infiles so we could analyze them. So thank you, Juan Martinez, for your hard work on that, who will be presenting next as well. So we ran this. I'd like now just to show you some of the results and some of the insights we got from this 2D modeling. What I'm going to show you now is for an R60 sample, a primary section factor of 80, a critical temperature of 500, and centers of 500 millimeters between the profiles. And what you're seeing here is a section factor of the secondary of 80 and a secondary of 160 section factor. And you can also see the varying widths of the hollows. So what you can see is as the coat back length running along the bottom 500, 1,000, 2,000, that yes, you do get the heating into the primary element begins to reduce. But you can definitely see there is definitely a huge impact for having different widths of those hollows. It's also clear that at a certain point, at a certain coat back length, the effects of the void or the void constraint become less and less prominent, and it seems to trend off to just a single point. And that seems to be the case for all the samples we ran. But what we did notice is that because you apply the coating of the primary section to the secondary, we were seeing a huge amount of differentiation between the performance of a section factor that had parity to the actual primary and one that was a lower section factor, or higher section factor, sorry. We saw that the behavior was much worse than we'd have expected for the coat back rule. And we also checked this for different fire durations, and as you might expect, all that happened is that trend is pushed up. You can see that based on the control, we went from maybe what was 1,000 millimeters and now up to 2,000 millimeters. And this was the same for R120. We're seeing a trend that we would expect to see. We also checked what would happen if your primary, your secondary section was at 500 millimeter centers or 1,000 millimeter centers. And what we found is as the primary increases in size and your centers are essentially getting greater, you can see that it actually has a huge effect on lowering the temperature. Now, what this means is I don't think that the 2D modeling is really capturing the longitudinal heat transfer within the primary. So really carrying out this sort of research in a 3D model is where I think we need to go next. But I do think we may have identified a shortcoming potentially in the guidance. So as you can see, with increase in the centers of the secondary, it pushes everything down. But what about the regular coat back rule? Like would the normal coat back rule on I sections give the same results? We did a bit of a sense check on this as well, and we ran another 9 models. Just instead of having the hollow, we replaced it with just a thin plate of different section factors, basically emulating an I section into a protected I section. And what we found is at 500 millimeters for an R120 fire scenario, with the worst case differential between the primary and the secondary, didn't see a temperature increase any greater than 25 degrees across the primary. So the fact that there's a void within the hollow and the coat back isn't quite as well performed. There does seem to be an area of research we need to do on hollows framing into primaries. It just seems like the I section one is very robust, but the hollows, we think we found something else. So just to wrap up, I'd like to sort of go into sort of the insights we found on this initial assessment, and then some of the next steps we would like to take and use SAFIR to look at this even further. So what we found is increasing the coat back length does reduce the average temperature increase in the primary. We know this is what the SCI document says, and we're seeing that same trend. So nothing's changed there. Longer fire durations increase the heating of the primary element. Again, something logical we expected to see. And the height of the primary, or rather the centers, definitely has a huge effect as well. And we were expecting to see that in our modeling as well. What we weren't expecting, however, is that width of the hollow to have such a big impact. And what we also weren't expecting to see such a large impact is the fact that the protection on the primary to the secondary seems to be much more sensitive than that of just an I section. It seems like the performance of the coating or PFP material just isn't as good as when applied to an I section. So what we found roughly is sometimes 500 millimeters would be okay, but this is for lower durations and when you're really getting parity between the section factor of the primary and secondary, or equal protection. In most cases, longer coat backs would be required, or even full protection, to ensure that heating into the primary element is kept at a safe limit. But further work, next steps, we are looking to publish a paper on these initial findings. So we want to make that available to the industry and the SAFIR community as a whole. So we're looking to do that very shortly. but we also want to investigate the thermal response in 3D. I think we need to do something similar to what the SCI did, and looking really at three-dimensional heating through those secondaries. But to do that, Thomas, Jean-Marc, I know we've been speaking about it, but 3D voids would definitely help us achieve that. So it's something we definitely want to look into. The next part as well is I think we want to look at a bit of a thermomechanical response of the steel as well. We want to understand that do these localized hotspots make a big impact or don't they? That's something else we'd really like to do. But another question again to the SAFIR community, doing a 3D solid model, we wonder if there's a simplified method of getting those thermocouple readings or node readings into, say, a shell model, just so we can be a bit more computationally efficient in what we're doing and start to address localized buckling that we might see and various profile types such as cellular beams, composite beams, beam and columns we'd like to look into. Obviously, there might be something we're missing in the modeling, so a fire test would also be really great to sort of validate all of these things we're seeing. And as many of you may be aware, this is sort of looking at a hollow that is framing into an end plate. We haven't looked at thin plate or gusset plates yet, which might mitigate some of what we're seeing. But again, we need further investigation to whether that is true or false. But it's some good news. We have already raised this with the ASFP in the UK, and they're really interested in progressing this work as well and looking at the possibility of updating the guidance once we've conducted this research further and may be able to provide us some support in actually getting this arrangement tested and if we've got an issue or not. So that's it from my side. I'd like to give a big thank you to the SAFIR community for letting me present, but I would also like to give a special thanks to Juan Martinez and Lefis Koutsolukas, I hope I pronounced that right, Lefteris, for the support in actually carrying out this research as well. Without their support, this wouldn't have been possible in the time frames we had. So thank you.